Okay. Now, we've got another question where this might be 6x plus 11 square root of x over, same question, 10x minus 15 square root of x. And somebody's looking at an example online that said, okay, well, this is 6x plus the square plus 11 square root of x, sorry. Now, it's not exactly the same, but I could write this as 5 square root of x times 2x minus 3. Okay. Now, that's a little different than the example you were seeing, but the point is, this still has a square root of x in the denominator. Okay. Now, I could shortcut the process in this case by saying, well, okay, let's just multiply both the numerator and denominator by square root of x. That's going to serve to get rid of the square root of x in the denominator. So we can say, okay, that's 6x. That's 11 square root of x over 5 square root of x times 2x minus 3, multiplied by the square root of x over the square root of x. Okay. And that's then setting out all the detail. That's what we're trying to accomplish here, which is understanding in detail what's going on. It's going to be like this. Now up here, I'm going to multiply 6x times the square root of x. Divided by that is 5 square root of x square root of x times 2x minus 3. Okay. And then that's 6x to the 3 halves plus 11x over 5x times 2x minus 3. Okay. So that could be done. Now, the reason I did what I did was because we're emphasizing using the distributive law to multiply this by the conjugate of this thing, by the 10x plus 15 square root of x. But in this case, it illustrates that if you factor the numerator, you get down to this. Now, in the example you were looking at, that example still left, don't need this, I'm not back there. That example still left a square root in the denominator. Okay, so that was not an example of rationalizing the denominator. It was an example of simplifying the overall expression. It stopped here without rationalizing the denominator. Okay. Okay. So nothing wrong with that example. Its goal was different than the goal here, which was to rationalize the denominator. But it could have been rationalized like this. Okay.
Question.
Yeah. Okay.
Question.
Yeah, okay. I want to talk just briefly, because briefly is all we got left, about the quadratic formula. And one thing that you have to know in order to do some of the homework. Okay, so I'm going to go over really quickly. It's going to be a short video, so you might want to watch it. Okay, let's say we got the equation x squared plus x plus 4 equals 0. I'm not going to write out the quadratic formula. We've done it before, and you're going to see it. So it's just a matter of remembering it. You don't have to derive it. But this gives us x equals -1 plus or minus the square root of 1 squared minus 4 times 1 times 4. All over 2 times 1. And you can do that arithmetic. You're not going to have any trouble with that. Okay, gives you this. Well, square root of -15, there's nothing you can multiply by itself to get a negative number. If you multiply any number by itself, it's going to give you a positive because either you have 2 negatives or you have 2 positives. So there's no such real number as the square root of -15. We don't let that stop us.
Imaginary numbers.
Yeah, and we get -1 plus or minus square root of 15 times the square root of -1 over 2, which is -1/2 plus or minus square root of 15 halves. But it's 15 times I over 2, where I is the square root of -1. And I stands for imaginary, so this is an imaginary number. Okay. What if I wanted to divide something like 12 plus 4i over 5 minus 3i? Now it's easy to multiply. I could multiply these, and you see how to do that, but the division is a little more challenging, okay? Nobody has any real trouble with multiplying. And this thing, actually, there's something that keeps popping up. Google Chrome does this, and I don't know how to stop it without blocking pop-ups, which I need for other stuff. Okay, anyhow, you get, okay, if you have this, how do you divide that? This is gonna look familiar. You multiply by 5 plus 3i over 5 plus 3i. Just like rationalizing the denominator, you have a square root in it, okay? And that becomes easy. That's exactly the same process that we got. And this gives you, well, I'm not going to multiply it out, but if you multiply out the denominator, you're going to get -4. Okay, no, you aren't. You're going to get you're going to get 16. I know what I did. Okay, your denominator is going to be 16. It's going to multiply out to 16, I think. And this is just going to multiply out by the distributive law. Okay, well, actually, let me finish it. Okay, this is going to equal, without going through all the details, 60 plus, let's see, you got 20i and 36i. I think that's 56i. And then you've got 12i squared over 25 minus 9. I'll skip some steps there, but you could fill them in and be exactly the same as what you've already done. Except, well, it's minus, sorry, and I said minus 9. Minus 9i squared. Right? Now, yeah, come on. Okay, so 60 plus 56i plus 12 times -1, because I squared, since I is the square root of -1, I squared is -1. So it becomes real, and down here the I squared becomes real. And this is then going to be 60 plus 56i minus 12 over 25 plus 9, which is 60, not 62, 48 plus 56i over 36.
No imaginary numbers.
And if you multiply this, so yeah, no, just like we did one square roots in the denominator, we don't have i's in the denominator. Also, if you multiply this by this, it's going to come out to give you this. So that's a short story. Again, arithmetic of complex numbers is not difficult, and it's easy to see where they come from. in the quadratic formula, okay? Now, all the implications tell you, I spent 2 years of graduate school after having a good foundation in theories of functions of complex variables, going deep into them, okay? And I didn't get, I barely scratched the surface. It's a foundation of most modern engineering. Okay, so these complex numbers are extremely important. Although yeah, you might never use them in depth, they're still important with applications you can understand.